All right, so Brian just introduced me. Thanks a lot, Brian. My name is John Chapman. Got my email address there, jc202@gmail.com. Send me an email if you want to talk about robots or something else pretty cool. I also have my GitHub page there. Everything that you see here for demos is on GitHub. So any source code that I show you today, you can go and see how that works. The one thing that is currently missing there is kind of robot schematics. So while I give you the code for the robot, I don't necessarily show you how to build the robot. So hopefully I'll get the chance to put that up there pretty soon to help you guys out. The other thing I did is I created a hashtag. If somebody wants to tweet and put Terminator Mickey, I'd really appreciate that. But that's what today is. Today's about Terminator Mickey. Yeah, so about me, Brian mentioned I do work for Symphono. Work with smart guys like Josh Springer, who just got up here and talked. We have a Chicago and Ann Arbor offices. If you like to work with smart people, let us know. The other thing, I think this is the third time we'll mention it today. I'm also co-organizing the Node Bots at CodeMash with Brian. Brian's been doing a fantastic job. He's got some really cool stuff lined up. And if you got to take it to CodeMash and you go to the pre-compiler, definitely come by and check it out. We're gonna have a lot of fun there. So this is gonna be a great time. All right. So what is JOHHNY-FIVE? JOHHNY-FIVE is an open source Internet of Things and robotics programming framework developed at Bocoup. JOHHNY-FIVE programs can be written for Arduino, BeagleBone, Intel Galileo, and Edison, Pinocchio, Raspberry Pi, SparkCore, TI Launchpad, and more. So that I just took right off the JOHHNY-FIVE GitHub page. Today we're going to be focused primarily on programming with the Arduino. That was kind of how it started, but since then they've adapted kind of an open I/O model that allows you to adapt to other platforms. Basically, it brings robotics to Node.js and JavaScript, the tool that we already know. Right? So why JavaScript? Right? First off, it's familiar. A lot of people here, we're all web developers. We know how to write JavaScript. Now we can use that JavaScript language to do fun things by building robots, and that's really cool. It's asynchronous in nature, which I think is really important for robotics because a lot of things we do in robotics are based on sensor inputs. When I detect that I bumped into something, take an action. If I'm looking at how far away something is, when I get close enough, then turn around. That asynchronous event-based, the next point, event-oriented, is really valuable and makes JavaScript a great programming platform. And the other thing I mentioned is the Node ecosystem, right? Node has modules for everything. So in one of the examples we have here, I say, I want to use an Xbox controller to drive a robot around. So you go onto NPM and you say, Xbox controller. And next thing you know, there's like 30 Xbox controller modules to choose from, right? Just about anything you can think of these days has a Node module to go with it. So it's really powerful in getting up and running with different things you might think of, right? Almost anything you want to integrate with, somebody else has probably started it for you, and you can build on top of that. And what you see here is actually a sample of what programming with JOHHNY-FIVE looks like. It's very simple, right? In this case, we're creating a new ping sensor. We tell it where the ping sensor is, and then that event of on change, we can call this function. All right. So I mentioned that we're focusing primarily on the Arduino. So this I took from the Arduino website. What is an Arduino? And they say it's a tool for making computers that can sense and control more of the physical world than your desktop computer. It's an open source physical computing platform based on a simple microcontroller board and a development environment for writing software for the board. One thing that's actually pretty important here is the fact that it's open source computing. And so what that means is all the designs for the boards, anybody can build them. And what you've seen is 2 of the 3 Arduinos I'm using here are actually built by a company called SaneSmart, which is a Chinese manufacturer, which puts out these Arduinos at between $10 and $13, which is really cheap and really easy to get into. And not that Arduinos are particularly expensive, and they'll probably cost you $20, $25, but having that option of such a cheap device is, I think, really appealing. Yeah. All right, so how does JOHHNY-FIVE work? I did mention that there's multiple options, but primarily in the case here, we're saying, how does it work with the Arduino? And that's the Arduino microcontroller. Now, the Arduino microcontroller is not a full computer. It can't run Node.js. Now, they do sell Arduinos that can run Node.js. That's, I believe the Arduino Yun can. But primarily, it's a microcontroller that only understands how to speak hardware, understands interrupts, pin outputs, and things like that. So to run JOHHNY-FIVE, it relies on another computer, a host computer, to run that logic. And then the way that they speak together, they do that over serial communication. and that protocol is known as Fermata. So Fermata is a protocol that says, how do I control hardware pins via a serial protocol? All right? And as I mentioned, you have the host computer. So in this particular case, all the programs we look at will be running off of this Mac, and then it'll be calling over serial Fermata to the Arduinos that you'll see over here. All right, so people might be interested in, what are some single board options? What if I want to build something that doesn't have a MacBook attached via a USB cable? What can I do? So the first one that comes to mind is the Intel Galileo. And what the Intel Galileo is basically a small Linux-based computer that has a software-based Arduino platform running on it. So it's not actually a real Arduino, but it rather mimics an Arduino in software. So natively, JOHHNY-FIVE supports the I/O built into Galileo. So if you build a Galileo platform, as soon as you create JOHHNY-FIVE, it says, hey, I'm running on a Galileo. I can control these pins natively. You can also do programs on Raspberry Pis and BeagleBones, right? So instead of doing Fermata-based communication, you can actually do GPIO communication, which will work on those platforms. You will have certain limitations like I2C compatibility is not really there. One that's kind of tough is actually things like servo motors can be troublesome on those platforms. So if you look at those platforms and let's say you're just doing LED control, they're very simple to do on those platforms. So depending on your usage, they may make sense to use. And as we went through in the beginning, there's also a lot of other choices for I/O options. All right, so the Fermata/Galileo example for how you'd initialize the board, right? So built in natively, JOHHNY-FIVE understands how to speak Fermata and how to speak to a Galileo. Whenever you run it natively, it'll say, hey, I'm an Arduino platform or I'm a Galileo platform. It'll automatically connect to that board. So you hear, all we have to do is we say, first off, we require JOHHNY-FIVE, and then we create a new 5-dot board. And that'll cause it to look on the system automatically and say, am I connected to an Arduino or am I running on a Galileo? And then upon receiving the ready event, we can say execute awesome. Right? Now a Raspberry Pi or another alternate I/O approach is a little bit different, but still very simple. So here you actually have to have a different dependency. So in this case, we're bringing in Raspi.io. Raspi.io is the I/O module for the Raspberry Pi. And when we create the new board, we have to say for the I/O, use the Raspberry Pi I/O. Other than that, everything else looks the same. So what the I/O will do for you too is it'll tell you what the capabilities of the board are. So that if you try to use, let's say, a servo motor, but your particular board doesn't support servos, you'll get an error saying, sorry, but that's not supported on your platform. All right, so this is going to be our first example bot, and this is the Terminator Mickey. So I had a fake story I was going to tell, but I'm not going to really tell that. And I was going to say that, this is my daughter's favorite toy, but I thought it was more fun, so I took it for my daughter, but I'm not really that mean. So what actually happened is we were out at a secondhand toy store, and we were just walking through looking for toys for my daughter, and I see this, Mickey Mouse sitting there. I'm like, that thing looks really interesting. I saw that it had a button in the hand. I saw that there was a switch on the foot, but it didn't do anything in the store. So I'm like, I don't know what this thing is. I don't know what it does, but I'm going to buy it. So I think it was like $6 or $7, right? So how do you say no to that? So I take the thing home. I rip it open. I break it apart so you can see kind of the Terminator shell up there. And I break open its chest, and I see this big, complicated controller board. And I think, oh, my God. So by this point, I actually realized that the reason why it didn't work in the store was the batteries were dead. So luckily, I was smart enough to be able to figure that one out. I put some new batteries in, I press the buttons, and the thing comes to life and starts moving around. So at first, I thought, I can go in there and program these servo motors and make it do all sorts of cool stuff. Now, if you can tell from this picture, this thing is super complicated. So when you go inside there, they're completely custom servo motors, and they don't use standard pins for servos. And there's about 9 of them inside there. So try as I may, I couldn't completely control the servo motor. So that's okay. I found something else cool I could do with it. So we'll get into what that is. So there's a few different technologies we have to know how to use with JOHHNY-FIVE to make use of Terminator Mickey. And you can see here, that's the GitHub repository that has the code for MickeyBot. All right, and I do have a little bit of a lie on here too that I'll get to. So there's a few components we're going to go through in order to make this MickeyBot come alive. There's light-emitting diodes, right? And that's what I use for the eyes, although one of the LEDs burnt out since I wired it up. So he only has one working eye, but that's okay. We're going to talk about relays. All right. So relays are something that basically it's a physical mechanism that allows you to connect a switch. So picture that you had like a rocker switch, an on-off rocker switch. When you flip that switch, it goes from one thing being connected to another. And a relay allows you to do that programmatically. We also have transistors. Transistors are another switching mechanism, but it's instead of having a physical hardware switch that moves like a relay, it's done completely inside of silicon. The other fun module we have here is an infrared motion sensor. So if you look up at the Mickey, you'll see it has this little bulb disc-looking thing. And what that is, it's much like a home security system when you have motion sensors in the corner. That's what's hanging off his neck. All right. And then I also have here a Bluetooth module. One thing you'll learn very fast when you start playing with hardware is things go wrong all the time. Like little simple things that you take for granted as a software developer, like, hey, I just write my little code and it runs and it works and that's kind of how it is. He used to be Bluetooth. There's still a Bluetooth module inside of him, but it doesn't connect to this computer anymore. So no Bluetooth for Mickey. But the later bought the Bluetooth module still works, so we'll still show you how to do that. And yeah, so about the Bluetooth module is I mentioned that you need a serial mechanism to communicate from ATA. That can be via USB like we'll do, but that can also be wireless over Bluetooth. There's other mechanisms as well. So I mentioned, one thing I'm working on now as a side thing is I want to use RF communication between two different Arduinos and then send from ATA over that. And that's something you can do, which I hope will be really cool, but I haven't got it all working yet. So anyway, light-emitting diodes. Basically, as current flows through the light-emitting diode, it emits light, right? And it's a diode, which means it's unidirectional, has one direction that it flows. Something of note is if you use a PWM signal, you can control the brightness of an LED. Now, what PWM means is it's a pulse width modulation, which means for a given signal, when you have high points and you have low points, pulse width modulation tells me how long am I at the high point and how long am I at the low point. So high point is on, or in this case it's 5 volts, and low point is 0 volts. So if you have your pulse width modulation set to 122, which is roughly half of 255, because it's a 8-bit pulse width modulation value, you want it at half brightness. So it's on half the time, off the time, you'll see a half bright LED. Now, the way you use an LED with JOHHNY-FIVE, it's really, really simple. So we do LED equals new 5.LED, and you give it the pin that you have that LED connected to, right? And then you get a very friendly syntax for how do I interact with that LED. I can turn the pin or that LED off. I can turn it on. I can tell it to blink at a certain interval. I can set its brightness if I have pulse width modulation on that pin, right? So all very simple interactions, and I hope everyone can see that. I realize it's at the bottom of the screen now, but hopefully everyone can see that all right. All right, so a relay, right? I mentioned that's an electronically controlled physical switch. The cool thing here is you have a low amount of power that can control a high amount of power. So in this particular case, we're using a relay to actually turn on the Mickey bot, right? So right now, he has a switch that turns him on and off. I cut that wire and then connected it through a relay instead. So what that allows me to do is via an Arduino, I can programmatically turn this Mickey on and turn him off. We're also using a second relay to simulate button presses. So inside of his hand, if you squeeze the Mickey hand, there's a little button in there that basically connects two wires. So instead of using a hand, what I've done is I've also used another relay that whenever you turn the relay on, it'll connect those two wires together, simulating a button press inside of the Mickey. All right. Now, the thing to keep in mind is a relay is a physical switch. So it actually, in this particular one, has to use electromagnets. So that actually physically moves a switch, and therefore it switches relatively slowly. So I think in this one you can do somewhere between 200 and 300 switches per second, which is pretty slow, right? So versus a transistor can do a lot more than that, right? So depending on what you're doing, that might seem like a lot or a little. For button presses, that's a lot, but yeah. So the way you use a relay, relays have kind of 3 pins that you connect, right? You have a common pin, a normally connected pin, and a normally open pin. And what happens is whenever you close that relay, it causes the switch to go from that normally closed to the normally open and connect those two. And then as you open it, it goes back to the other point. All right, so that in order to use a relay, you just say use pin 2, close the relay, and open the relay. It's honestly that simple. Right? I mean, the thing I really want to stress today is this is simple, right? I used to be really intimidated by hardware, like that looks really hard. But, you know, via things like JOHHNY-FIVE, we can do it, everyone can do it, and it's actually really simple. Until you light things on fire, which I've done a few times, but that's all part of the fun. Transistors, right? So we just talked about relays, and that's physical switching mechanisms. Transistors is a way to do that via semiconductor. Again, a low power signal control a higher power signal. And because it's a semiconductor, it means it's fast. Yes? Yeah, so I don't know exactly. I'm not sure if the voltage is going to matter too much. I think it'd be more about the current, which I was going to get to in a second. Is this particular transistor can only handle about 1 amp of current, right? But because the relay is a physical switching, you can do a lot more than that 1 amp. This particular relay, I'm not sure what the max current is that it supports, but I'm pretty sure it's over 20 amps at least on this one. But I'm sure other relays can handle much higher, right? You'll see people doing things like connecting home appliances via relays. You're not going to try to do that via a transistor, but you can do those sorts of things with relays. So your particular relay might have different ranges of what it can support. But the good thing to keep in mind is higher current, you want to use a relay. Lower current, faster switching, that's where a transistor comes into play. And the thing of note for the transistor is actually to get enough power to power the relay, I actually had to use a transistor to turn the relay on and off in this case. And that's why I needed both. And that's the point right there where typically you're going to handle less current with a transistor versus the relay. And basically the way the transistor works is you have your collector and emitter for the current flow, and then you have the base which says allow the current to flow or don't allow the current to flow. All right, infrared motion sensors, right? That's that little bulb thing on the right, and you can see it around Mickey's neck there. And basically there's a couple different ways this works, but the way we have it set up to work is whenever it detects that there's motion, it'll set the trigger to high, saying I've detected that there's motion in front of me. There's potentiometers on the back that allows you to control the sensitivity, but that's basically all it's doing. It says I have motion or no, I don't have motion. Now the way that we interact with that via JOHHNY-FIVE is there's the sensor module. So inside the sensor, what we're going to say is create a new sensor. It's connected to pin 10. The type will be digital, and I want to pull it on a 25 millisecond frequency. All right. So digital means I only have two values, yes or no. Right. There's also other things that are analog sensors, like how much light is being emitted. Right. You do that with like a photoresistor that we'll get to later. So that would be the difference between an analog and a digital sensor. So then what we see here is we can have two options. We can say on that polling interval, tell me whatever the data is, and that's what the data event is. So every 25 millisecond, here's your current data value. Or what you can say is whenever the data value changes, raise this event to let me know, and that's what you see here with the sensor.onChange. All right, and I did mention the Bluetooth module. Again, we're not going to see it here, but we'll see it later. In order to use Bluetooth, all you have to do inside of your JOHHNY-FIVE code is, you remember when we said create new board? It automatically checked to see if there was a connected Arduino or if it was running on a Galileo. What you can do here is you can say my port, where my board is actually on this Bluetooth channel. So what you see is where it has /dev/tty dot. The part that comes between that and the dev B is the name of the Bluetooth module. So for any Bluetooth module, you give it a name. So in this case, I called it MickeyBot. And then when it connects, it tries to make a Bluetooth connection to the Bluetooth MickeyBot. Again, this one broke, but we'll show it in the next demo. Demo time. So, everyone see this all right? So this here is the MickeyBot source code. I don't want to go through the whole thing. You can get the code on GitHub if you'd like. But you can see kind of the concepts we were just talking about. So we see here that we require JOHHNY-FIVE. Using JOHHNY-FIVE, we create a new board. So in this particular case, we're using USB. So it can detect automatically that it has a connected Arduino on the USB port. You can see here the olden days. It used to support Bluetooth, but the Bluetooth module broke, so no more Bluetooth. All right? And then we have a couple different things. So we have a power relay. what we're going to do is, upon detecting that there's motion, we're going to turn the bot on. All right? And then we have a second relay, which is the dance relay. And what we're going to do again is, if we detect motion again, we're going to make him dance. All right? And so we're using relays for both of those mechanisms. You can also see that we have eyes LED. That's the LEDs we're going to use to turn on his eyes, at least the one that didn't get burnt out. And then we have a motion sensor for detecting that motion. All right? So you see here, much like the code we talked about, dance relay, that's connected to pin 3 on the Arduino. Power relay, that's on port 2. LEDs are plugged into port 12, and our motion sensor is plugged into port 10. All right? This is how you have to connect JOHHNY-FIVE sensors. To start up, we're going to open the 2 relays, all right? And we're going to turn off his LEDs. Now, what you'll see is, so this motion sensor, right? We set it up right here. It's a new sensor. Upon receiving data, we're going to check what our current state is. And basically what we're going to say is, I don't want to go into this too much, so we're getting lost in kind of the details, but the first time we detect it, we want to call power relay.close. This is going to turn the bot on. The second time, if the power is already turned on, using the isOn property on the power relay, we're going to trigger the dance operation. If we look at trigger dance, all it does is it closes that relay, it waits 1 second, and it opens that relay back up, simulating someone pressing that button and releasing it after 1 second. All right, so let's see this thing dance. Let's see how it works. And let's see if this works too here. All right. So this is a Node application. So I did all the code in index.js, trying to be pretty simple. So I call node index.js. So it's connecting to that USB serial port, and it connected. All right, so this is the Mickey. Now, I don't know if Brian's moving or not, but we'll have to see if it triggers the motion here. So there it just triggered. We can see that it's now spinning up because it detected that there was motion. And if it senses another motion, Mickey Mouse is in the house. Right? And so it should keep monitoring for that motion. So if I move again in front of it, it should trigger a longer dancing, a dancing session. Now I do have to hold it because it has a lot of weight in the back to hold the Arduino. And if I let go, it'll fall right over. So, and there. So it's really complicated. I mean, you can tell all the motion it's doing. It's moving its head, it opens its mouth, it moves its legs, it moves its arms, and it keeps going. So that's the Mickey bot. All right, now let me just try to run this again so I can reset it so it doesn't fall over. Yeah, so that's a great question. So I mentioned that, let me just disconnect this. So I mentioned Fermata, right? Fermata is a protocol to control pins. So what I did is I loaded, and you know what? I'll show you actually. I don't know if I can make this any bigger. So the fonts don't change. But if you go on the Arduino, you'll see that they have examples that come with it. Inside those menus, you'll come down to this thing called Fermata. Right? If I select standard Fermata, that's the program I load onto the Arduino. So what that does is when it spins up, it looks for a connection on the serial port of the Arduino, and then it then listens for that protocol saying, take pin 13, set it high. So the JOHHNY-FIVE just translates, LED.on and says, take pin 13 and set it to on.
So that's just basically a pass-through translator.
Exactly.
That's on my
Yeah, now there's other I/O mechanisms it speaks as well, but Fermata was the first, and that's everything we're showing here. Yeah?
The mechanical part, how do you control it? I see you say you have a relay that goes on and off. How do you say move it on?
So yes, that was my original goal. That then became like a really big stretch goal. So usually what ends up happening is you have kind of standard servos that kind of have 3 pins. You have a power, a ground, and a signal. And it's easy to intercept yourself and say, you know, turn to this degree, right? So that's the way you would usually do something like that, is you use servo motors. You can tell the position to go to. So turn, you know, you can think of each of your joints as a servo motor. So you'd say this one would control this direction, right? And this one would control this. So you'd say, JOHHNY-FIVE has built-in support for animation of servos. So you could program keyframes of servos saying, go to the 90-degree position and then go to the 180-degree position. So you can actually create dance moves inside of JOHHNY-FIVE.
This is not part of the Arduino, right? It's not part of the board, right?
I'm not doing that here, right? That's how you would do that if I had standard servos. But this is all custom servos that to interact with.
You have to hack the output, right?
Yeah, exactly. So instead, I hacked, like, I mean, there's just wires everywhere. So instead, I found, all right, well, how does this thing get triggered? Let's solder custom wires onto the board to trigger the actions, instead of just saying, how do I control this particular servo? Yes. Yep. Yep. So the REPL is just for the console input, right? So I was originally using that while I was debugging. So I could do things like, I'm exposing the power relay, the dance relay, and the eyes LED. So from my console, I could type eyes-LED.off and see it reflected in hardware. But this is just the read, emit, print loop for the console. I can delete this and run the exact same code. Everything still works. It's not needed for the hardware. Yeah, so right, so it's what there are. So things like, we talked about motion sensor on data, right? The way that that's set is there's always a value that's being written on that pin, but JOHHNY-FIVE itself, you set up a polling interval to check that pin. So JOHHNY-FIVE, when we create it, which I haven't set here, but if I were to go here and say, that's going to set up a polling interval of 10 milliseconds, which is not on that REPL loop. That's a totally separate timer that JOHHNY-FIVE sets up for you, which is 25 milliseconds by default. All right, anything else? All right. Example robot number 2, this one I call the Clawbot. So what this is as I was starting to play more and more with robotics, I wanted kind of some variety to play with. And you know, somebody mentioned here First Robotics League. I forget who that was, talking about looking for mentors. They do some really, really cool stuff, right? And what you see here is this was actually a platform that one of the First Robotics Leagues used to use. I forget exactly, it's not the top level, but it's one of the middle levels. And I was like, that looks really cool. It's got all sorts of cool motors, cool things to use. Now, when you buy the full kit for First Robotics, it has a brain that comes with it and a controller, and just the way I work, I'm like, I don't want all that stuff. I want to do it myself. I want to figure out how to hack that thing to do what I want. So what I decided to do here is buy just the frame, ignore the brain, ignore the controllers and all that stuff, and then control it with an Arduino. So that's what I did. So the goal here with this bot is drive the Clawbot with an Xbox controller. So in order to do this, there's a few different things we have to know how to do. We have DC motors, all right? So DC motors give us motion. There are motor controllers, and what a motor controller does for us is it takes a DC motor, which you basically turn on and off, and allows us to control it as if it was a continuous servo. What that means is we can say, turn clockwise, turn counterclockwise, spin at 50% speed, spin at 100% speed. We're going to use the Bluetooth module this time, so as long as it didn't break since this morning, we're going to get to see the Bluetooth module. The important thing to keep in mind with the Bluetooth module is Bluetooth has a latency of about 500 milliseconds. So because I'm driving it with an Xbox controller and the table is really small, it might fall off the front or the back of the table. It's not necessarily just because of my driving, it's also the latency involved, all right? And then we're going to use the Xbox controller. So the Xbox controller is just a node module to control using the Xbox controller. All right, so a DC motor. You apply voltage to the motor, motor spins. If you reverse the polarity through the motor, it'll spin in the opposite direction. All right? So if you're trying to drive this robot around, you need to be able to control if it's going forwards or going backwards. That's where the motor controller comes into play. That's what gives us the control to reverse the polarity for the current that's going through that motor. All right, so the continuous servo, I mentioned we need to have a motor controller. You see the picture, that's the motor controller I'm using here. That's actually a product that's sold by the same people, Vex Robotics, that makes this kit. Basically what that does is when I connect that, it takes a 2-pin motor and turns it into a 3-pin continuous servo. Right? So now in order to drive it, I can use the servo library built into JOHHNY-FIVE. I create a new servo, I set the pin that I connect it to, I set the type to be continuous, and in this case, I also have to set a PWM range. So what this means is different motor controllers have signals to tell it how fast do I spin, what direction do I spin. And this particular motor controller uses a 1000 microsecond ping, or sorry, high signal to say spin at the lowest level, and then a 2 millisecond, basically 2000 microsecond to spin at the other end. So that's basically the full spectrum of 0 to 180 degrees.
That's in the motor control.
Yes. So basically what you do is you say, motor controller, I'm going to send you a signal for 1 microsecond, and that's going to tell it, okay, I need to set my servo to 0. If I send it 1500, that sets it to 90, right? Because it's at 0 to 180 degrees. So because that sort of logic is in the motor controller, these things get to be a little bit expensive. So these particular motor controllers that I'm using, they cost $10 a piece, right? Versus the DC motors only cost a few dollars, right? And that cost can really add up, but it's adding some kind of smarts for us.
So the motor and the controller must be matched.
Well, so a DC motor is just, I apply current to one end, it spins one direction. I apply current to the other end, it spins the other way. A DC motor will always work that way. What you do have to make sure of, though, is that the current that you're using is compatible with the motor controller that you're using. But I could easily swap out these DC motors with other ones, and the same motor controller could drive that as well. All right, and then so for the API, we say servo.clockwise 50%, right? That says spin clockwise 50%. You put in CCW 50%, it spins the opposite way at a speed of 50%. And they can also stop that motor. So again, a really simple API to interact with continuous servos. All right, so this has nothing to do with JOHHNY-FIVE, but I want to mention it anyway. So we're going to use a USB RF-based Xbox controller to drive our robot. It's just a Node.js Xbox controller module. So npm install Xbox-controller. And you can use that here. Now, a side note, this particular module only works on the Mac. In theory, it works on Linux, but that was a real big pain. So to get it to work on Linux, I actually wrote my own controller that works. It's going to provide us our control. All right, demo time. So again, index.js. Everything should be one file. I'm trying to keep it really simple. So again, require our JOHHNY-FIVE. So here you actually see we're going to use Bluetooth. So in this case here, we're saying I want to connect to the Clawbot Bluetooth module. Again, it's just a string-based name for where that device is. This is a bunch of stuff related to the different sensors on the Xbox controller can provide different values, so it requires a calibration step to know if I'm full forward, full back, etc. So skipping all that. All right, so I lied a little bit. It's not all in one file. So the Clawbot is actually the module that I'm using to drive this thing. So I originally set it up so I could drive with an Xbox controller. I could drive it programmatically. I can use different mechanisms of driving. So I put that as a separate module, which is the Clawbot module. So what you see here is optionally you can provide the board to use, which is what we're doing. So I want to skip that. So here we see that we mentioned a left drive motor and a right drive motor. Those are both the continuous servos that we're using. So again, new 5 servo. What board am I connected to? What pin do I use on that board? What's the PWM range? And what's the type? In this case, they're continuous servos. And again, there's also an arm that's going to raise up and down, and a claw that opens and closes. Those as well are just DC motors connected to motor controllers for continuous servo. All right, so things like when I tell it to drive left, I basically take the left drive servo and I say spin clockwise at -1 times that speed. I want to take the right drive and do the same thing. I spin counterclockwise at that speed. Again, all very simple things. I want to take the claw and I want to open it. It's .cw, turn clockwise. All right, and if we go back here, so this here, the Xbox controller, basically just say, on event of the left stick moving, process its current state. On the right stick moving, process the state. And then one thing I've done here is I actually process this on an interval basis. Now, the reason why I have a configured number of updates per second is there's a serial connection that goes to the Arduino that runs at 57,600 bits per second, right? So when I use the Xbox controller, I can change those inputs really fast. And so what I found is if I don't cut the rate at which I'm sending control to the Arduino, you basically lose control because I overrun that bit rate and I'm not getting all my signals sent to the Arduino. So that's one thing to keep in mind when using that serial connection is you don't have unlimited bandwidth. If you keep trying to run things, you might run into trouble. So I had bots before where I was trying to turn and it just ran straight into the wall. All right, so let's get this thing going. And one thing I'm also very careful about now is if you looked really closely, you see that there's some burn marks on this robot. This is one of the ones that caught fire. And basically what happened is in transport, I have a little breadboard here and one of the wires came loose. I connected the power, it shorted the wire, sparks flew. So be very careful, right? So I always check every time I turn it on, make sure everything's plugged in correctly after that experience. All right. Yeah, really. All right, let's see. Let me get a little ambitious here. Let's see. All right, let's see if this one works. Now, just so you know, I do have the most failures with Bluetooth. It doesn't always connect right away. Let's hope it actually does this time. So again, node index.js. I see the little Bluetooth signal saying it's connected to something. All right, and we connected to Bluetooth. So no wires, connected via Bluetooth. So what I have to do first is calibrate the analog sticks. Now I got all the range in, I'll hit enter, and I'm ready to go. So let's see if it works. If I move the two sticks forward, it drives forward. The way I have it set is if I hit the right bumper, I switch the control to be the arm here. So I can raise and lower the arm like we saw. And I can open and close the claw. So let's see if I can do this. Let's put it back to drive. Now I can't actually see the cup, so there we go. Through no help from the audience at all, I grab the cup. All right, so we do that. We drive backwards. Actually. And we drop it off. So there's one on each side. And then there's just gears that connect both wheels. And that's the Clawbot. And the other thing, too, that I haven't cleaned up yet on this one is the Xbox controller module will sometimes keep the process running. Here it's shut down, but sometimes Node.js will just keep running if this is still working.
How does that say the Xbox is signaling
Yeah, so everything in Node is running on this Mac. So I took the USB module here, I connected it to my Mac, and so I'm then using my Node program reading the sensors from this module. So this reads that I'm pressing forward halfway, and it turns that into and says, using Fermata, tell JOHHNY-FIVE to the Arduino, set the motor to 50% clockwise. All right. Yes?
And if you wanted to eliminate the Mac from that loop, you would use one of those all-in-one solutions we were talking about earlier.
Yeah, so I mean, you have multiple options. The Galileo is a great option. One thing that I don't like about the Galileo is this Arduino that I'm using has a built-in linear voltage regulator, right? So all the logic that has to run on Arduinos and most of this hardware has to be at 5 volts. Let's see if I can do this real quick. So if we go back to this robot here, you have this battery pack on the backside. That battery pack is a 7.2 volt nickel metal hydride battery pack. So in order to take that 7.2 volts and convert it to 5 volts for the logic on the Arduino, you have to have some sort of voltage regulator. There's a voltage regulator built into the Arduino that can take up to 25 volts and convert that to 5 volts for you, all right? The problem is the Galileo doesn't have a built-in voltage regulator, so you have to use an external separate voltage regulator to get the 5 volt input, because anything outside of like 5.25 and 4.75 volts, and you're going to fry your Galileo. So for that reason, I tend to gravitate towards the Arduino because it's so friendly to get up and running. Yes? So everything kind of has issues, right? Like one of the things I really like is taking a Raspberry Pi with an Arduino, and you can connect serial connections between the two of them. That as well has issues. If you want to do pins directly for the serial pins, natively the Raspberry Pi is going to use 3.3 volts for its serial connection, and the Arduino uses 5 volts. So again, you have, how do I synchronize those two voltages? So to simplify that, I actually use a USB connection between the two, and then that's always going to be 5 volts over USB. So if you just put the two together on one board, you can have an all-in-one solution, meaning no separate computer running it. So that looks like a BeagleBone, and what is that one? Oh, that's a brand new one. I haven't played with that one at all yet. So I believe the BeagleBone as well does not have a voltage regulator.
It does not. I bought 10 of them for 20 cents off of Amazon.
Is it a linear?
I don't know. It just takes my 9 volts to 5 volts. It gets rid of the less than used.
Yeah, that's pretty cool. Yeah, I mean, the voltage regulator I bought I think was $5, so apparently I don't shop from the right place.
This one's awesome. This is the amp. It's wireless also. Like this one's wireless. It runs Linux and it runs automatic right out of the device. So you plug it in.
Yes.
Just get going. This one, this is the entire thing. There's a Wi-Fi chip right in it. SD card. This is just the development board. But this thing by itself is wireless and do everything that the Arduino does. It's a little more expensive. How cool is that? That also runs.
Very cool. Yeah, so no. Yeah, way to go, Brian. Yeah, so BeagleBones are actually really, really cool from a JavaScript perspective. Like things that people talk about with Raspberry Pi is they think of it as Python first, right? It comes with Python programming environments out of the box. Now, you can run Node on a Raspberry Pi, but it's always been known as kind of a Python-based platform. The BeagleBone, there's a few cool things about it. One is the creator of the BeagleBone is from Ann Arbor, right? How cool is that? And then the second thing is it was built with JavaScript first mentality. It comes with a programming language for you, which is called BoneScript, which is Node. It's Node-based I/O mechanism for that. And what it actually includes is if you ever use the Cloud9 IDE, it's basically a remote IDE using JavaScript, so an inside browser IDE. And then everything you do runs directly on the BeagleBone. So you open up your little IDE on your Mac and you say, LED set to whatever, although You're not going to use LED unless you use Johnny-FIVE, which it does support. It's just really cool to get up and going that quickly with the BeagleBone. So that is one I definitely use and do enjoy. And I'm going to go steal one of your voltage regulators. Yes?
Back up for a second. You're talking about using the Raspberry Pi and the Arduino together to serial port. What can I learn more about that? Because I'd like to do something. Using the Raspberry Pi for, say, a database.
Yep. Yeah, I mean, so you see everything I'm showing you here with just new board? It's that simple to get up and going with the Raspberry Pi. So it natively, if you just take a USB cable, plug it from the Raspberry Pi, plug the other end into the Arduino, do new board, you're already speaking Johnny-FIVE to that board. So I mean that's what I've done, and it's really that simple. That simple, right? I mean obviously you got to do your npm install Johnny-FIVE, right? That's going to pull down all the node modules that you need. For the Raspberry Pi, it needs to have it uses node serial port, which is a, what's the term for the compiler? What's the compiler? GYP compiler. So it'll do a JIP compilation for the Raspberry Pi. The Raspberry Pi is powerful enough to compile it locally, and then you're good to go. So you had a question about the Yun, I believe. The Yun only has 64 megabytes of RAM. So if you do npm install Johnny-FIVE, it'll die on you while trying to compile node serial port. So in order to work around that, I had to go find a pre-compiled version compatible with the Yun, download that separately, load that pre-compiled module into Johnny-FIVE, and then use that. So also because there's only 64 megabytes of memory, there's a lot less power involved in a Yun than you get with a Raspberry Pi or a BeagleBone. A BeagleBone has a gigabyte of RAM, right? They're quite, and it's a 1 gigahertz processor, or actually it's 512 megabytes of RAM and a 1 gigahertz processor. So it's very different computational. It's a lot more powerful. All right, so example bot number 3. So this one's the tracker bot. So what this one is I wanted to build a little robot that would be able to follow a line, right? I see people doing that all the time. You can always do line followers. And my thought was, how would I solve this problem, right? I didn't want to read about how other people solve the problem. I'm doing this for fun. I'm not doing it for how well it works, right? As long as it works and I had a good time doing it, I'm happy. So what I decided to do here is I was going to use LEDs to shine down a light and then use photoresistor to detect how much light there is, right? The idea being something that's white is going to reflect more light and something that's black is going to reflect less light. I figured that's all I need to do to follow a line. And this particular bot, you can probably tell, it's 100% Lego. So I'm using Lego Technic kits. So this is not using Mindstorms or any of that stuff. It's an Arduino using the chassis built out of Legos. All right, so things that we need here, LEDs. We talked about that before with the Mickey bot, right? And that's what's going to shine down the light to tell what it is below us. DC motors. So that's the things that turn the wheels, that make us move. In this case, we use an H-bridge motor controller. All right, so we talked previously about motor controllers and continuous servos, and those things costing $10 a piece, which are really expensive. An H-bridge is basically a cheaper solution to that same problem, and we'll talk more about it. But an H-bridge, the one I have, I bought for about 50 cents, and if you're the lucky winner here, you actually get an H-bridge. So one little story, when I first started playing with robotics about maybe a year and a half ago, that's the kit that I bought. That's the first thing that got me started. So I'm a big fan of that particular kit there. And the other thing we're going to learn about is photoresistors. All right, and a photoresistor is just, depending on the amount of light that's shown through, it changes the resistance to the voltage that passes through it. And that's how we're going to be able to detect, is it a lot of light or a little bit of light? All right, so an H-bridge, right? This is the circuit that allows us to control the voltage in a bidirectional manner. So what you see there is you see that there's a motor in the M, and you see that there's 4 different switches. So basically what ends up happening is as you control that H-bridge, you can close the S1 and the S4, and that'll cause current to flow through in one direction. Alternatively, you can close S3 and S2, and that'll cause current to flow in the other direction. And that circuit, using, these are actually transistors, is what allows us to control if we go forward or if we go backwards. It also amplifies voltage, right? We talked about transistors earlier. which basically says I can use a 5-volt signal to control a higher power motor. In this particular case, I'm using a 11.1 volt battery pack, and I'm driving those motors on there with over 11 volts. These particular motors are 9-volt motors, but they haven't blown up using 11 volts, so more power. This particular H-bridge that I'm using is the L293D H-bridge, right? So built by Texas Instruments, 50 cents a piece, pretty cheap, and they support natively 2 motors. So every one includes 2 different H-bridges, so I can use one chip and then drive both left and right motors. And again, they're very inexpensive. So what you see here is a truth table, right? So what ends up happening is you have to use 2 different pins to control how the H-bridge is going to spin, right? So what you see here is there's an enable pin to turn it on. So what I've done is I've actually hardwired the enable pin directly to the 5-volt signal, so it's always on. Then you're going to have to tell Johnny-FIVE the 2 pins you want to use for control, one of which it knows as the PWM pin, and one is it knows as the directional pin. So what ends up happening is when one pin is low and the other pin is high, it turns the motor one way. When the other pin is high and the second pin is low, it turns in the opposite way. Any other combination and the motor's not spinning. All right? So what ends up happening is Johnny-FIVE will support pulse width modulation natively. So you say spin the motor at 100 out of 255, right? Because it's an 8-bit value for the PWM signal. And one of the pins will always be set in the direction, either high for one way or low on the other. And the opposite will be fluctuating on and off, right? So basically, if the one pin is set to low, it fluctuates up, it starts to drive. It fluctuates low, it stops driving. Fluctuates high, it starts driving again. And that's the way Johnny-FIVE is actually driving that motor and allowing it to control the speed. And so what you see here is we create a new 5 motor. You give it the 2 pins, the PWM pin it'll use, and then the direction pin. And then for this particular H-bridge module, you have to say to invert the PWM signal. And what that means is basically when I set full blast in the opposite direction, it should be low all the time. So it inverts one direction, it's always high for full speed, and one direction, it's always low for full speed. And the reason why, again, is this truth table. Low is clockwise, high is counterclockwise, right? So only if they're opposite is it going to spin. I hope that makes sense. And then again, the way we drive it is forward to spin one direction, reverse to spin in the opposite direction, and again, stop to stop that motor. Photoresistors. This is an analog input used as a sensor. The more light that's detected by this item, the less resistance there is inside of that resistor. I don't remember what that last bullet point was anymore. But basically what we're going to do is we're going to have 3 separate photoresistors along in a line. So I can tell as I move, as I go over the white part, I know there's going to be more light. So as there's more light, there's less resistance, meaning there'll be a higher voltage. So the way the analog signals work is it detects the voltage on that pin. So 5 volts is a full-on, I believe it's a 10-bit in a 10-bit value. So that's 1023 will be your value for the most amount of light, and then 0 will be the least amount of light, right? So it's just a voltage 0 to 5 volts, which is right there. So it provides input between 0 and 1023. 0 volts is a 0 value, and 5 volts is a 1023 value. So the way this works is I create a new 5 sensor. Before we talked about digital sensors, when we did the motion sensor, now we're talking about analog sensors. So on the Arduino, the analog sensors start with an A value. So A0 is just the first analog pin on that Arduino. And in this case, I'm also, again, specifying a frequency to say, pull that pin, check the voltage every 10 milliseconds. So in this case, again, it's the same on data and on change value. So I can get notified whenever that value changes or whenever I get a new value, which is every 10 milliseconds. Demo time. So this is another case where I started with a Bluetooth module because Bluetooth is awesome. And what happened is I put the baud on the line, it immediately went right off the line. It's like, what's going on? And the thing is, because of that 500 millisecond latency, I had already completely lost the line by the time I even knew that I lost the line. So it turned out to be really hard to follow the line without that USB cable giving me that immediate feedback. So again, you see the new JOHHNY-FIVE board. I'm creating a JOHHNY-FIVE board. I create new LEDs. I immediately turn them on, right? Because I want to shine the light down, and then I'll constantly be reading those values. I create the motors like we talked about. Pins 10 and 9 invert the PWM. And then I have the right motor on pins 3 and 2. Again, the same thing. A0, A1, A2. Those are our analog pins. And then all I'm doing is I'm saying create the 3 line sensors, which are our photoresistor sensors. So here's what's going to happen. When I spin this thing up, it's going to wait for me to press a button. It's then going to drive itself forward for 2 seconds and then drive itself backwards for 2 seconds. The goal there is, because I'm reading the amount of light that comes off of the board, depending on the room I'm in, there's going to be ambient light. So that means the light sensors that I read from the photoresistors is going to change. So I need to calibrate it for every room I'm in. So what I do is I drive over that line and back off, and then it figures out the range of this is the highest value I saw, this is the lowest value I saw, and then it basically takes an 80% value and says, anything over this, that's the line. So drive forward to 160, wait a second and a half, and then stop, turn around and drive backwards. All right, and so all we're doing here is the left sensor on change, process that value. Right? Whenever I get a new value, I just do the whole logic and I see, am I on the right side, am I on the left side, am I in the middle? And based on that decision, I either go full speed forward, I turn around a little bit one way if the line's on the left, or I turn around the other way if the line's on the right. And that's all we're doing here. Oops. Wow. You guys are a little anxious over there or something. I don't know. You know what? Let's see if I let's start this again. All right, that looks better. All right, I don't want to do that right now, so let's just do this. All right. So this will be our course for the demonstration. It's just a poster board that I took some black paint and put a black line on it. I want to show it moving. And this one I also put a power switch on the back. So the Arduino itself is going to be powered by the USB cable, but the motors are actually powered via the battery pack that I mentioned, running at 11 volts. So to make it drive, I have to turn on that battery pack. All right, let's see if this thing works. Index.js. So I got to be quick about this. So to run, I have to press enter, and I'm not very quick. So you can see there that the bot went forward, went backwards, and it says the calibration is complete. If we go back to this screen here, it basically gives us what our minimum value was that we detected, what our maximum value was that we detected, and then it sets a threshold for how it knows if it's on the line or off the line. The 80% value? Yeah, that was just trial and error that seemed to work, and I went with it. So hasn't failed me yet, so it's got to be the right number, right? All right, so I now placed the robot on the line, so I should be able to follow it all the way to completion if it works. So I'm going to hit enter, and it's going to start driving along that line. And when it reaches the end, it detects that there's no more line and it stops the robot. So that's the tracker bot. And so someone asked me at the start of this when they saw me setting this up, they said, how do I know that you didn't really just go in there and write a program that says go forward, turn, go forward, go turn, you know? That would work too. I'm always doing the same thing. So It would be a pain in the ass, but you know, it'd be one way to solve the problem. So I've never actually tried going the other direction. So I'm going to give that a try now and see if it actually works. It can't drive backwards, no. Oh, it doesn't work. Too much of a turn. Yep. So there you go. Demo gods say no. Almost. Yeah, and there you go. There it's done. Yeah, I'm caught on something. Thank you. Sorry, what's that? Color? So, I mean, what I would do for color is I'd probably use some sort of a color filter and then have a different photoresistor for each one of those filters. So the filter could say only allow blue light through here, and then if you put it behind there, you could get that same effect. So that's just me thinking on the spot. There might be other better ways to do it, but that's what I would do. You might be able to. Yeah, I've never tried something like that, but.
There are some color sensors available also. Biggest problem with that is they really don't want, they want to be included. So the color sensors actually have a little box.
Yep.
Tiny box that kind of sits in, so it's only looking at the one color. So you might be able to.
Right, so I think what Brian was saying is that they sell sensors that will detect for color, but they need kind of a enclosed environment to not be influenced by other light. So they have a small box, you're saying, to control the light that's around it, right?
You got a close enough grab, you probably see.
Okay, so if you're trying to follow a line and you had it right on the ground, there shouldn't be other light interfering, and that would probably work. All right, so some common things that I didn't show here. The first one is definitely a servo motor, right? I talked about continuous servo and using that to drive forward and reverse, or clockwise and counterclockwise. But the MickeyBot internally uses servo motors to control, you know, moving its arms around. So it's very common to see things built using servo motors. Also the ping sensor, right? So a ping sensor is an ultrasonic sonar detector, so it can tell how far away things are. That's also very commonly used and something to definitely check out if you want to be playing with robots. I definitely recommend that. So I do want to talk about those briefly just to show how easy they are to work with. So again, a servo, create the new servo, give it the pin it connects to, and then you say to the angle you want to turn to. It's that simple. Ping sensors. There's a module called ping. You tell it the pin is connected to. Upon receiving a change in value, JOHHNY-FIVE lets you know here's the current distance or how far away it is. So in this case, we're saying what's the current inches for the current item that's in front of that ping sensor. They do. So you have inches and you have centimeters. So, all right. You can also work directly with pins, much like what you've probably done if you ever programmed the Arduino directly. You're probably used to working directly with pins. You can skip the abstraction of motors and pins if you'd like to, and interact directly with those pins. So here we're saying, take this pin and set it to a PWM pin or an output pin or an input pin. That's also available for you to use. All right, and there's lots of classes. Now, one thing that I kind of wish I shown is, I'd say one of the more recent JOHHNY-FIVE contributors I know is Mr. Brian Geneseo over here. He's recently started contributing. One of the really good ones is, I went through how I determined I was going to look for a line, right? Brian's like, yeah, but how do you do it better? Okay, so what Brian actually implemented is an infrared sensor array that can use infrared instead of my LEDs or my colored LEDs to detect for that line. And that's now been added as a new module inside of JOHHNY-FIVE. So also check that out. There's a local contributor adding that to the project.
Better because ambient light doesn't affect food.
That's my understanding, Brian. I know that it has to be really close, but I don't believe it's as impacted by ambient light as my LEDs are here.
That's because I know it's not the infrared that I care about as much as the boards that are arrayed. So you can get a board with 6 sensors on there. And then with Johnny-FIVE, the abstraction, the cool thing is, instead of saying, okay, I want to read these 6 different things, I can just get one value between 0 and 5,000, let's say. And that tells me where I am in the sensor array. And that's one of the things that the fact that it's IR, I mean, it doesn't, I don't think it matters as much, to be honest.
Yeah, you know what? I'm going to test that out now and see if it matters. But I mean, I think it might. I think it's really cool. I mean, the one downside, I think, to that sensor array is compared to using an LED, which costs pennies, and a photoresistor that costs pennies, there is some cost in getting the sensor array. It's like $10, I think they were.
Yeah,
so that can add up a little bit, but it's a really nice, tight package. So it's pretty cool. I also put on here other sensors I've played with, I've used. You can test for what's the current humidity in the air, right? What's the gyro positioning? Do I tilting left or right? I have a compass sensor. I can detect flames. I can detect if there's water or not, right? I have shock sensors, so upon something being nudged, I can get a sensor input. There's lots of fun stuff to play with here. Other times people have said, yeah, you're having a lot of fun, but I want to do something practical. I don't want to just have fun, you know? So it's like, all right, maybe you want to refill your dog's water bowl, right? Get a little water sensor. You can tell when they run out of water. Use a servo motor to turn on a valve that dumps in, or use some sort of a valve that dumps water into the bowl. Turn it off when there's water in the bowl. That's very easy to do using Johnny-FIVE. And questions?
How long would a flame sensor last after it detected the flame?
So what I haven't done is I haven't taken that sensor and put it directly in the flame. So I don't know how it works. I just played with it and said, wow, it works, and I left it at that. So I don't know. Sorry.
There's a certain type of light that fire puts out.
Really?
That is detecting. I don't know anything beyond that, but the flame sensor can be affected just by lights around us. So if you put it closer to light, it's just looking, I think. It's more sensitive to a different type of light that
No, so I mean, basically what Brian said is it's sensitive to the type of light that comes off of the fire, and that's how it actually detects if there's a flame or not. And you can also confuse it, he said, by putting it close to like a light bulb. In the back. Yeah, so one thing of interest is I mentioned, the ping module, right? And basically what ends up happening is that the way that the ping works is it's very specific to timing. So what ends up happening is it sends a signal out that sends a signal to the closest object, and it bounces back. And it actually measures the amount of time it takes to send that signal and get it back. Via JavaScript over that serial connection, you can't get that kind of accuracy. So what they've done is they've extended Fermata to be able to sense that time and send it back over Fermata. So Fermata is open source. You can go grab it and add whatever you want for custom pieces. But just understand that if you add a custom piece that requires Fermata code change, you're limiting the people who can consume your module, right? Because now they also need that Fermata change. So, but you can do that kind of stuff.
You also find in Bluetooth, which goes over the,
I don't think so. I mean, I've never tried to do something like that, so I shouldn't say it's impossible, but I don't think you'll be able to compile Arduino code on the Arduino. So what you see is the Arduino IDE. What ends up happening is when I have that C code that's written there, that's compiled on the Mac, and then the compiled code is then sent over to the Arduino. Now, maybe you could have compiled code that somehow you sent, but I don't think so. And there were a lot of hands.
So I noticed that you were using Bluebird for promises.
Yep.
Which is great fan. But still, promises, even with Bluebird, are a little bit slower than callbacks.
Mm-hmm.
Johnny-FIVE, are you just adding promises because it's a lot easier to deal with asynchronous stuff, or is it actually promise-based with Johnny-FIVE?
No, Johnny-FIVE is not promise-based, so it's using callbacks.
Do you have issues with the
It's a stylistic choice that I make because I like promises.
Yeah,
So
did Bluebird, the promises, did that add a significant latency problem, or was that?
No, I mean, the latency that you see there is the Bluetooth module is going to have a half-second to second delay in latency. It doesn't matter what you're doing, right? And then so the Bluebird promises, I think you can run something like 100,000 promises on this particular Mac per second. So you're talking about like a microsecond. It's not going to add significant delay. So I wasn't concerned about the performance impact of promises. I just like the way it looks.
Probably worth noting, we don't tend to see these latency issues over USB, right? The latency issues tend to be over Bluetooth.
Right.
And so if you're over USB or serial in general, those things aren't affected. There's a Fusio buzzer, and we can get up to about I think 2,200 hertz in the notes that we play before we have any issue with network getting in. But the moment you take that and put it on Bluetooth, you can't create a signal that is anything replicable.
Right, and the only thing I'll say over USB though is I've run into issues with bandwidth, right? So that kind of introduced latency because I oversaturated that serial bus, and then my next command couldn't run. So you don't have the timing delay of I want to send a signal to the Arduino, but you still have a limited amount of bandwidth to work with.
If you use a board that doesn't use serial,
that's true.
Then you're actually talking directly to the board. So then something like redeemable black, you're actually talking to the board directly, and there's no latency to serial.
Right, even the Galileo, I believe, is direct. So. And the good thing about the Galileo is it gives you good support. So most of the modules we talk about, they don't support one thing or another, right? So they don't support analog reads, that's a common one. Or they don't support I2C, all right? Arduino supports everything, and Galileo supports pretty much everything. So those are always good platforms to work with. Were there other questions? Yeah, I'd say local. Micro Center is kind of local, at least if you live on the east side, but I buy very little local. So if I go to Radio Shack, I cry every time I go to the register. It's just, they cost about 10 times as much as they should, right? So there's lots of great sources on eBay. There's lots of great sources on Amazon, Adafruit, SparkFun. So that's where I buy everything online. Yeah, it's just, you can go to Radio Shack, but what they have is limited, and it's just super expensive, so. Right, I mean, I did the same thing, right? I had a component, I ordered it online, I get it home, I fry the thing, it melts. I'm like, I can't waste this whole Saturday, so let's go to Radio Shack and pay 10 times as much, but I try to avoid it, so. Really? How many of them come back working? So I have lit an Arduino on fire before too, so it is possible. So that's part of the fun, I say. So were there other questions?
How many hours did it take you to accomplish your plan?
So here's the thing with hardware, right? Things can be finicky. The thing that took me the longest with this particular robot, well, first was building the chassis. So Legos take time to plan it out, make sure it fits everything. Where's the motors go? Where's the battery pack fit, right? I don't know if you noticed this, but I had the two wires, the USB cables, connected to the Arduinos beforehand. So I like SaneSmart, they're cheap, but I've had issues with these particular ones. And I sent emails to SaneSmart, and they told me like, oh, that's awful, how can we help you? And they say, oh yeah, that's your problem. So basically what happens is these two USB cables, one works with one Arduino, the other works with the other one. So when I was first trying to drive on the bot, I was connecting to the other USB cable. I spent hours saying like, failed to connect to Arduino, failed to connect, cannot find device. And then I'm like, take this Mac and throw it. Like, all right, these stupid Mac, where's my Windows machine? That'll fix this problem. So I go to the Windows machine, it's like, oh, fatal driver error. Like, so, and then I'm just randomly, as I'm kicking things and destroying things in my house, I say, you know what, let me just try this other USB cable. Everything works. I wasted 4 hours basically breaking things in my house and another 4 hours cleaning up my house, but things like that can drive you insane. So that's actually where I spent most of the time. The code that you see, I mean, it took a half hour to an hour for most of these programs. So they're really simple. It's just little things with hardware that end up being gotchas that'll drive you crazy. So, yes?
Run a simulated robot and programming and
That's a really cool question. Now I want to go do some research. I don't know the answer to that. But does one exist? I mean, yes. I mean, we could definitely make it. So, right. So one thing that we talked about was the I/O modules. You can do Raspberry I/O for Raspberry Pi. There's no reason, and actually there was a blog post that Rick Waldron retweeted today talking about all sorts of different I/O mechanisms, things that run in the browser. You know, how do I do like RF-based Arduino to Arduino communication as an I/O module? So there's no reason why your I/O module couldn't be simulated. It doesn't have to be a real connection. It could be a simulated robot. Now, I don't know if anything like that exists, but that sounds really cool. And one thing I do want to mention that Brian was talking about, we're trying to gauge interest, right? So I love working with hardware. I love working with robots. Maybe some of you guys are interested too. We were talking about doing kind of a community project together to work on doing a custom extension for JOHHNY-FIVE that will work via the Scratch programming language. So something to get kids involved in robotics. So let's say we had some sort of event around here locally. Maybe we could work with a local organization like the Hands-On Museum. Have kids who can program these robots using Scratch. You know, that's something that we think would be really cool. And you know, we're kind of interested, what's the community feedback? Is this something somebody else would want to help with? People interested in this at all? So I definitely see some hands. So that'd be really cool. I think that'd be a really cool thing to do.
Just playing with the idea right now, but the idea of just even having a community project that we can all contribute to, they kind of take it outside of our monthly meetings a bit.
Yep.
And then, you know, I'm sad that these robot kits that we're bringing to CodeMap, we got it down to about $28 a kit. That includes the Arduino, 2 servos, a whole bunch of other stuff. You know, I put together 100 kits for CodeMap. It's so cheap that it doesn't take much donation for schools to get their hands on $10 $300, $10. And the problem is with second graders is JavaScript and Node is a little too low level still. Scratch is designed specifically for kids. So we can get to a point where we can create some bindings, use the abstractions that JOHHNY-FIVE gives us, and make it so Scratch is the actual interface that we're working with. Just create a servo, turn it on, turn it off, like you would an animation in Scratch. How cool would that be? And then I know the principal of my daughter's school already runs this. And so I can imagine this is not so talk to us. I think this is the type of thing that we as a group would like to expand to more community level.
Yeah, I think it'd be great. Set up a GitHub project. We all can contribute. If you're interested, you know, for now, let's talk about it. You can send an email to Brian. We can talk on the meetup page. There's a place for comments. We can communicate there. But let's get that conversation started because it looks like there's some excitement, and I think it'd be really cool to work on. So I think that'd be fantastic. Were there any other questions? All right. Well, thank you very much. That was JOHHNY-FIVE and programming robots in JavaScript.